So today's lecture, in fact, this whole week, we're going to pick up some topics where we're going to try and understand more about how the things that we've been doing actually work. The first topic here is layout. How do H-stacks and lazy V grids and scroll views and all that, how do they work? How do they decide where to put everything in there? So we're going to talk about that, and then we'll have a little demo. Similarly, view builder, right? We've had this cool little view builder thing. We know that it's just a function that returns some kind of view, but we also know it's kind of cool in that it's a list of views and it's got if-thens in there and local variables. So how does view builder? Now, I'm not going to talk about really how view builder is implemented, but I'm going to talk about how you use it and how it works. So layout. How is the space on screen assigned and apportioned to all those views that appear there? And it's actually an incredibly elegant little system and very, very simple. And it has very strong rules to it that make it so it's incredibly predictable. Pretty much 100% predictable what it's going to do. And it's 3 steps. The first step is, of course, views are offered some amount of space. Now, your content view, the things at the top of your app, is offered the whole screen, right? That's the starting point. But then once you start making H-stacks and V-grids, now you're being offered less and less space as you go down there. A container view, like an H-stack or V-grid or whatever, is offered a certain amount of space, and it turns around and then offers it to its children with some algorithm. And now, when it does that, number 2 is crucially important, and really, it's really the thing makes the whole system really work, is that views, after they're offered a space, even if they're like a text view or an image or something like that, they choose what size they want to be. The only person that can choose the size of a view is that view itself. There's no way to force a size onto a view. Views choose their size, and they choose a size based on the space that's offered to them. All right, we're going to talk about how they do that. But this inviolable rule that they choose their own size is a lot of what makes it so this system is completely predictable. And you don't get these weird cases where you don't understand really what's going to happen. Nobody is forcing anything on anybody. But then once the views choose their size they want to be, now the container view comes back in and it places them, right? The H-stack decides, are they all, placed evenly, or some of them placed over more to the left and some to the right? That's up to the H-stack to position them. So positioning is done by containers. Size is chosen by the views themselves, and they're positioned by the containers. That's the way the system works, and it always works that way. And it has a really nice little protocol for doing this dance, which I'll kind of show you. I'm not going to implement it, but I'll show you what it looks like when we get to the demo. So let's talk about some of these things and how they make decisions to do all that stuff. And the basic ones are H-stacks and V-stacks. They're the most basic layout here. And they take the space that's offered to them and they try to divide it up to all the views that are inside of that. Now, the key to H-stacks and V-stacks is this idea of how flexible is a view inside of the H-stack in terms of using the space. Some views are not very flexible, like they basically want a certain amount of space, you give it to them. And other ones are incredibly flexible, like a rounded rectangle. It can be tiny, it can be gigantic. It's anywhere in between. Very, very flexible view, but other things are less. So let's talk about some examples of flexibility here. An image, like image system name, whatever, very inflexible. It wants to be the size that it is, doesn't want to be smaller, can't be larger. It's the least inflexible view out there probably is image. Next, least flexible, texts. Okay, text want to fit their text, right? They're mostly want to be that size. But in a pinch, if you make them smaller, they'll allow them to be smaller and either do that minimum scaling. Remember we did the minimum scaling to make the thing fit, or they'll just put ... They'll cut off the text and put ... on the end of it. So they're pretty inflexible. They want to be the size of their text, but they'll scooch down a little. And then, of course, very flexible, rounded, rect, and circle. All the shapes tend to be completely flexible. You can put anything you want in there. This flexibility is the key to how H-stack and V-stack work. After the first least flexible view is offered its space, the H-stack gives it that space from the space it has, and then takes the rest of the space and moves on to the next least flexible view. In other words, the least flexible views are taking space first, then the next least, until there's hopefully some space left over, and then you can give it to a flexible view if there's there. Or you might get too big won't even fit. All the views said they wanted more space than even fits in there. And then the HDAC has to decide what to do. Does it go back to the somewhat flexible views like the text and say, actually, I'm going to offer you a little less space because I ran out of space. And it might accept it or not. So it can adjust. So it's a little dance back and forth until it can get them all to fit. And they may not all fit. If you try to force them to be smaller than they can possibly be, like if you put 100 image views in an HDAC that's pretty small, it's just going to spill out the sides. And then after the HDAC or VStack has sized them all, then it sizes itself to fit them. So that means it might be smaller than the space that was originally offered to it if they're all inflexible views, right? And they're less space. Or it might actually be larger. If it couldn't fit them all, then the HDAC might end up being too big. Again, the HDAC is just a view. It gets to choose its own size, just like all of the things inside of it, and it might choose to be too big if it can't fit the things. So that's it. That's how HDAC and VStack work, a very predictable, sensible way to do it. And this is one of the most powerful and most elegant parts of all SwiftUI is all this laying things out. When you're doing HDAC and VStack layout, there's a couple of little views you're going to put inside them that are really valuable. And you've already seen one, which is the spacer. The spacer uses all the space that's given to it in both directions. So it kind of fills up extra space. So it's great in an HDAC where you want one thing on the left and one thing on the right. Then you put a spacer in the middle and it'll use all the extra space. It's a very flexible view, the most flexible view, right? And the other one that we haven't seen is divider. Similar to spacer in that it uses all its space in the crosswise direction, but uses minimal space in the direction you're going, right? Horizontal stack, minimal space, and it draws a little gray dividing line. And the divider it draws is kind of platform dependent. On a Mac, it might look a little different than on iOS. Maybe on an Apple Watch, it looks a little different. But those two things, spacers and dividers, you'll be using those in HDACs and VStacks to group your stuff and separate them and all that. So this least flexible thing, I told you that HDAC and VStack go to the least flexible guy first and then the next most flexible guy. And then, well, you can override that with this view modifier called layout priority. The layout priority by default is 0. It's a floating point number, it's 0. You can set it to anything you want and put it on a view. And if it's the one with the most priority, it gets the first chance to get the space out of the HDAC. So here I have an HDAC that has two texts and an image in between. The top text is important text. I want to see all of that text. So I've given it a layout priority of 100. The other two, the image and the text, they have a layout priority of the default, which is 0. So when the HDAC goes to lay these out, it's first going to offer space to important. And important can get all the space it needs to draw the full word important, because it's the most important one. Then it's going to go to the image and text and say, well, the image is the least flexible, so it gets the space next. And then finally, it goes to this unimportant text, which is tied with image, but it's more flexible than image, so it's the last one. And so if there's barely any space left, it might say unim ... instead of unimportant, because it doesn't fit. Or it might get truncated completely. All right, alignment. So we already saw this with HStack and VStack. You might put things in an HStack and it's laying them out horizontally. That's great. But then do they sit in the center of the HStack, or are they up towards the top of the HStack or down towards the bottom? And we saw that there's this alignment argument that you can provide to a VStack or an HStack that says which way you put it there. And you can align not just by top and bottom, but by leading edge and trailing edge. And notice that I say leading and trailing, not left and right. And I don't know if I explained this, but why do we use leading and trailing in SwiftUI instead of left and right? Because some languages, text goes the opposite direction. Arabic, Hebrew, they go right to left. So you want the things you're laying on your HStack to go with the text. They want to go right to left too. So leading means the edge from which text flows. Another kind of things you can align on are text-based lines. Let's say you have a bunch of text, maybe the texts are not exactly the same size, big font, small font. You want their baselines to all line up. And so you can do that in there as well. It's even possible to have your own custom alignment on anything you want semantically. A little complicated for this intro course that we're taking here, but you can kind of look in the documentation if you found some reason you really need to line it up. But it's a very flexible system. Let's talk about lazy HStack and lazy VStack. What are those lazy things? Well, the lazy primarily means that it's not actually going to lay out the views that are not on screen, right? It starts laying out the views until, oh, now I'm off screen. I'm outside of my bounds. I'm not going to lay them out anymore. So you could have 1,000 items there. Maybe it's all the songs in your music library. You don't want to have to go lay out 1,000 things just to show the first 7. But once the guy starts scrolling, now you got to start laying out the other ones. The lazy H-stack and V-stack do that. One thing about the lazies is they don't take up all the space inside of them, even if there's flexible views inside of them. So that's different than an H-stack and V-stack, right? If they have flexible view, they'll use that extra space. These ones don't. So you're almost always going to put these inside a scroll view because they're going to scrunch down to the size of the things inside of them. And you're generally not putting flexible things in there unless you have things that constrain the flexibility, like aspect ratio or something else that's going to make it be an actual size. So that's lazy H-stack, lazy V-stack, mostly, again, for scrolling lists of things. And then there's lazy H grid and lazy V grid. We've already seen this, of course. We used a lazy V grid to lay out our cards. I'm not really going to talk about it too much here, but it's similar in that it sizes itself to the things inside of it. So you usually put it in a scroll view. Yeah, you already know how to use this. Not waste our time talking about this. There's another thing called grid. Now, grid doesn't have an H or a V in it, so grid is a view that you use to lay out things in both directions. I like to think of grid as my spreadsheet view or a table view. You know, you have a table where it has certain columns. That's kind of the way a grid works. And the grid's mechanism is a lot about these view modifiers, dot grid this. So things like dot grid column alignment can make it so that everything that's in the third column over is all left aligned or right aligned, things like that. So we're not going to really use grid in this course. It can be valuable if you're building a table-like thing like that. You might use them in your final projects. When you do go to try and discover how to use grid, definitely want to make sure you go and find these view modifiers that start with dot grid, because that's really about how you make this really work. Then there's scroll view. We've already seen this, super simple view, and it uses all the space that's given to it. So a scroll view always takes all the space offered to it, but then it puts the thing inside and lets you scroll around on it. 100% obvious what that does. There's another super cool view called view that fits. View.fits, its view builder has a list of views, usually only 2 or maybe 3. And what it'll do is check out the size of all of them in the size that's offered to the view that fits, and it chooses the one that fits the best. So a classic example of this is you have a view that fits, and in this view builder, you put an H stack with your items and a V stack with your items. And when the phone's in portrait, it ends up using the V stack because it fits better. But when it's in landscape, it ends up using the H stack. It's really cool little idea. Another one this is really good for is dynamic type. When old people like me on our phone, we go set our type to be really large, that can make it so that now things won't fit horizontally, right? The text is just too big, and so it needs to now be vertically. And this will do that automatically. In other words, this is not looking at portrait and landscape or anything like that. It's actually sizing its views and seeing which one fits best. Form and list, an outline group and disclosure group. We're going to talk about these later in the quarter. These are sort of super smart V-stacks. V-stacks that know about things like selection, right? Selecting items in the V-stack, or hierarchy. Maybe I have data that I can click on a little, disclosure thing, and it'll show me deeper children information, then click and go even deeper. They're very powerful, but let's wait till later in the quarter and we'll talk about them. And finally, you can build your own ones of these using this custom layout protocol. I'll show you again in the demo briefly what that looks like. It's probably rare that you would do this. We're actually going to build our own combiner view that lays out our cards, but we're going to do it in terms of other ones rather than doing the full layout protocol. And by this layout protocol, I mean the thing on the very first slide. Offered space to your views, they pick sizes, you position them, that whole dance is all this layout protocol. It's a really beautiful, simple protocol, as you'll see when I show it to you. Then there's Z-stack. I didn't put Z-stack in the same breath as H-stack and V-stack because, of course, it's a little different. You're stacking these things now, towards the user, from the device up towards the user, and so the sizing is a little different there. the Z-stack has its alignment and it's going to put things in there. But the important thing to know about Z-stack is if even one of its children is fully flexible, like a rounded rectangle or something, then the whole Z-stack gets full flexibility because it wants to give as much space to that thing as it can. And really in Z-stack, one of the key things to understand is what's going to be the size of this Z-stack? And it's going to be the largest thing that needs to fit. That's Z-stack is obviously going to fit the largest thing. And if the largest thing is fully flexible, then the Z-stack is going to be fully flexible and take all the space ever offered to it. And that's sometimes what you want, but sometimes not. For example, you might have a little text right there, and you want it to be Z-stacked or stacked on top of a rectangle. You want a rectangle around it. But you don't want the Z-stack to use all the space. You want the Z-stack to size to the text and just have the background only behind the text, right? Well, you wouldn't do that with a Z-stack. You would do it with this background view modifier. So the background view modifier takes a view, a single view, not a view builder, by the way, a single view, although you could obviously create your own bar, which was a view that was a view builder inside of it. But anyway, it takes a single view and it puts that view Z-stacked behind the view you're modifying, but the sizing is all determined by the main view, not the thing in the background. So background is like a two-man Z-stack where the sizing is the one in the front. It determines the size. And similarly, there's another one called dot overlay. It's the opposite. The two-man Z-stack where the thing in the front is a slave to whatever's in the back. So for example, here I have a circle that's got an overlay of a text. In that case, that's going to be a flexible view as large as can be. So that would be similar to a Z-stack. Now, in these cases where you have an overlay and you got that text in there, obviously it could be in the center, but you might also want it leading aligned or top aligned or whatever. So this has also an alignment that lets you say where you want it if the thing that's determining the size is bigger than you. Background and overlay, very simple. Two-man Z-stacks, who is in charge of what the sizing is. Whereas Z-stack, it's always the largest of the one in the stack is the Z-stack. Modifiers. Why am I talking about view modifiers here in layout? Because really, a lot of modifiers are essentially like little layout engines, if you want to think about it that way. I mean, some of them, like let's say foreground color or font, they're not layout things. They just, whatever size is offered to them, they just pass it on to the view they're modifying, right? Because they don't do anything. But other ones like padding, they actually change the space that's available to the thing. If I put padding around a text, now the text has less room to put itself in. So you can think of padding as a simple little layout thing that takes the space offered to it, scrunches it in a little bit, and then offers that space to the thing inside. So if you had a padding 10, then it would offer the view that's modifying it a space that's the same size as it was offered, minus 10 on all sides. And then the view that's returned by the padding 10 would choose a size for itself that's 10 points larger than the thing inside. So it does the dance with the thing inside. The thing inside still gets to choose its own size, and then the padding adds 10. But the size it offers that thing is the size it was originally offered to it, minus 10. See how the dance goes? Size offered, go in 10. This guy sizes himself, add 10, back out. I might be bigger than what I was offered if that thing inside wanted to be big. Another example of a modifier that is kind of like this is aspect ratio. So the view that's returned by aspect ratio takes the space that's offered to it. It picks a size that's either in the aspect ratio inside what was offered to it. That's the dot fit. Remember, we had content mode dot fit. Or it picks a size that's as big as possible, where one edge is the largest size, and thus it'll be bigger than the size offered to it. That's the dot fill option, bigger, dot fill. So that's the difference between dot fit and dot fill. And once it's done that, then it's going to offer that space to the thing inside, and then whatever that thing picks, it's going to be in a, it's kind of centered in a view that is the right aspect ratio. So aspect ratio and padding, these view modifiers, they act a lot like V-stacks and H-stacks and things like that. They do this layout dance themselves. Let's talk a little bit about views that take all the space offered to them. Of course, we know about shapes, and we're going to do our own shape. It's going to do this. But other views also can do this. For example, our card view does this. Whatever space we give our card view, it draws in it. And for example, the way we make it be the right aspect ratio is we view modify it with an aspect ratio modifier. It creates a view that's the right aspect ratio and offers it to our card. Our card uses all of that space. And we already did a little bit in there to make it use as big a font as possible, right? We just chose a really large font, and then we use that little, scale, minimum font scale, text size scale, whatever that modifier was, and it shrunk it back down to fit the space that was offered to it. But if we think about the view that has all our cards, what if we took that thing, took all the space offered, and then picked a size for the cards that would fit perfectly in there? So we wouldn't have to scroll around if we had too many cards. And if we had a few cards, the cards are nice and big. So that would be an example of getting a lot of space and then trying to pick an arrangement that makes it work. How would a view that would want to do that, how does it find out what size it is without doing that whole layout dance? Because that layout dance, it's got a lot of work to do. Well, the answer is you can put your view inside another kind of container view called a geometry reader. So a geometry reader, using it looks like this, geometry reader. It's a view that takes all the space offered to it, sees what size it is, and then passes that onto its subview, right? Its view, its content view, along with this little proxy, this geometry proxy that says what the size it found was. Here I have a geometry reader. I'm wrapping it around. See the 3 green dots? That would be my view that I want to know the size of. And the proxy is telling me things here, how big the space is I was offered. This frame and coordinate system is a rectangle with coordinate space, and this coordinate space could be the local coordinate space of the view, or it could be the global coordinate space of the device. And then this safe area insets thing is interesting. That's saying how much of the space that was offered to it is being cut off because like the notch at the top of the phone gets in the way. So that gets automatically removed, but you get told what it is in case you're saying, I want to draw under the notch anyway. So I'm going to draw outside the safe area there. So that's how Geometry Reader works. Really, really simple. It's just like a wrapper view that passes the size offered to it. The only trick with Geometry Reader that's important to understand, it uses all of the space offered to it. It's really the only way it can work, right? Because the whole idea is it tells you how much space was offered to you, so it has to use all that space to see what its size is. So that's in red here. Some people, they forget about that and they're trying to make a view small, but then they're like, oops, I forgot. I put it in a Geometry Reader and now it's big as the space offered. That safe area thing, that's the notch, all those things. Another way you can ignore the safe area is with the view modifier edges ignoring safe area top. And that'll make it so that Z stack will draw outside of the space offered to it on the top into a safe area like the notch. It's not just the notch, by the way. Sometimes you're put in a navigation view, on a phone, sometimes you can navigate around, you can hit the back button to go back. Well, where that back button is at the top of the screen, that's a safe area for the views inside of it. But if you were like navigating through images, maybe you would want those images up underneath that back button up there. You want them outside the safe area, you can do that. This edges ignoring safe area will basically make it so that view, it ignores any safe area on the top or the bottom, whatever. So let's get a demo here. We're going to do that thing I talked about of having the cards go ahead and use all the space offered to them. This is where I told you when we would get back to this lazy V grid and I would explain this better because I had to rush it at the end of, what was that, lecture 2 or something. So let's talk about what's happening with this grid item. We'll go back to what I was saying at the time, which is that really we'd love it if lazy V grid would just let us specify the columns like 3 and there would be 3 columns here. But we can't do that. Can't specify 3 there. And the reason for that is we don't want to just specify how many columns, we want a little bit of control over the columns. So instead of this being the number 3, it instead is an array of these things called grid items. These grid items define each column. So here I have 1 grid item in the array, so I have 1 column. Still working fine. Here's my card. There's 1 column. And if I have 2 grid items, then I get 2 columns. And however many grid items I put here is how many columns I'm going to get. These ones that have no arguments are actually having the argument flexible. So flexible is the default. argument to a grid item, they're flexible. These things can be as big or small. They're allowed to be whatever. And this has some arguments too, but you can also have fixed is another one here. So if I say dot fixed and maybe, I don't know, 40, really tiny. See, I fixed this column to be 40, and that's just that first column. I have two columns. So that's how grid item works. One thing I do want to take a second to look at is this fixed. You see this fixed right here? I'm going to open that up in the documentation and show you that it's actually an enum. It's a case in an enum for this thing called grid item.size. So here's grid item.size. That's the argument to a grid item. And there it is. There's the three cases. Flexible with minimum and maximum size, fixed with a fixed size, or this adaptive thing that we ended up using in lecture 2, right? Case, case, case. These are enum. What are these things called? The associated data for those cases, right? When you see things that start with a dot, like this, dot fixed, it's not always going to be like a static function on a type. It might be an enum. So let's go back to what we had before, though, which is we were using this adaptive item, adaptive, and we had a minimum size, 65 or whatever. And we also had the spacing in here being 0. So I've set the spacing here to 0, and that's the spacing in between is this one, and the spacing over there, that's 0, that's the spacing in between the rows. Why have I set this to 0? Because our goal is to pick the right size cards that will fit perfectly in here. So I need to take the spacing out of the equation. And why is that? Because this spacing is platform dependent. On an Apple Watch, might be one thing. On a Mac OS, it's a different thing. The default spacing, I don't know what it is. So I can't put it in my math of how the cards would fit. So instead, I'm setting the spacing to 0, and I'm going to pick the space so they all fit 0. And then the padding, I add as an extra little padding down here after the fact, after I've already divided the space up to fit the right number of cards. Here's a really valuable debugging tool when you're trying to figure out which view is using which space. These H stacks and V stacks are laying things out. Where is everything? And what you can do is go to some views, like maybe this button, and put a background view on it. And a color is a great background. So color is not only the argument to foreground color and all that, it also behaves like a view. Okay, color behaves like a view, which is really convenient. So I can set background. Remember, background means put this view behind me, but use my size. Just put it there and see, oh, there is the bounds of that view. And I can do it with other things too. How about the VStack itself? Let's go here and say dot background dot yellow for the VStack. So there it is, the VStack. You see how it's padded, the padding makes it in from the edges a little bit. This yellow is a little bit in from the edges. If I put this background on the padding view, then it would go all the way to the edges. And this is important to understand that the padding view is a different view than this VStack in that it's put this extra padding around. Doing this little background thing and plopping it around on various things inside and outside of padding will really help you understand what's going on. Let's do the same thing up here with our cards. So I'm going to put my cards here and say dot background. What colors I got left? Blue, green, red. I can see the red. So here is my cards. It's a lazy V grid, so it has fit itself. But you can see the scroll view is big, right? It holds it's big space. And when I scroll, whoop, see how it's scrolling around inside my scroll view. So putting background colors, ooh, really, really cool way to just see how all these things laid out your world. Get those out of there. Our goal here is to make these cards fit. That's this number right here, right? 65 makes it so that they fit. If I change this to 95, now they don't fit, and I have to scroll. Everybody agree with that? So I need to pick this number so that things fit. And once they do, then I won't need this scroll view. And if I took off the scroll view now and just use my cards, I have a big problem. Again, this VStack tried to fit everything, couldn't fit it with that minimum width, so it actually pushed the shuffle button that was right here off the bottom of the screen because it's in a V-stack with this very tall thing, and I don't have a scroll view anymore. So shuffle button's down here somewhere. Can't see it on screen. So I want to pick this 95 to be smaller when I have so many cards. But when I have a few cards, I want it to be nice and big so I can see my cards really well. So I'm going to do this with that geometry reader. Let me make this close because these lines are getting long. I'm going to put a geometry reader here around my lazy V grid. It's got this little geometry proxy here. And the only thing that this has really done is it's made it so that this view here takes all the space offered to it. That wasn't true before. Lazy V grid, it sized itself to the cards. But now geometry has made it takes all the space. But the great news is it's going to tell us what that space was, all that space in this geometry thing. And we can use this to set that card. So I'm going to create a function to pick that size. Func grid item width that fits. And it needs some information here, some arguments. One argument that it needs is how many cards to fit. So that's the count. And another argument it needs to fit is the size. What space are we trying to fit in? So that's a CG size. And finally, it needs to know the aspect ratio to fit it into. So if I have those three pieces of information, then I can return 95 or whatever the right number. I can calculate the right number to put there. So let's call that up in here. I'm going to let grid item size equal calling this function grid item width that fits. And what's the count? How many cards do we have? Well, that's our view models cards.count. And what's the size we're fitting in? Well, this is where that geometry proxy comes in. Remember this geometry proxy we have here? This is what it looks like in the documentation. It's got the frame in local or global coordinates, and it's got this size right here and those safe variant sets. So we're going to use this size that comes in our geometry proxy as the size we have to fit our cards in. And the aspect ratio is the aspect ratio we've been using, which is 2 to 3, a 2 to 3 aspect ratio. And this size is our geometry proxy's size. Let me space this out so you can see this better. Everybody cool with that call right there? I'm calling that function. We still have to implement this thing, but I'm just calling it to find out what it is. And then instead of having 95 here, I'm going to use this grid item size. Sorry, one other thing. This grid item size that fits function, it has to return a CG float. Now this should be working exactly the same as it was before because I'm returning 95 down there. Sure enough, it looks like it's doing that. And if I go down here and say 65, then they're smaller. That's great. Shuffle button fits on there again. So how am I going to calculate this 65 to be the right number? Normally, I actually in past quarters have copied and pasted this in here. I'm going to go ahead and type it in because I see that a lot of you are still following along. And by the way, if you're following along, you don't need to be doing it for the homework. I still think it can be a valuable way to understand what I'm doing, but you don't have to follow on for homework. So what's going to be my strategy for calculating what fits? So here's how I'm going to do it. I have some space that's offered to me. And first I'm going to try to use one column and see if it fits. Now, depending on my aspect ratio, it might fit or it might not fit. The card might be so big that it won't fit. If it won't fit, now I'm going to try two columns, okay, and keep that same aspect ratio. Now they might fit. If that doesn't work, I'm going to try 3 columns, 4 columns, all the way up to 1 column for every single thing I have. So that's all I'm going to do. That's my strategy. It's really simple. Just going to try every possible column count until it fits vertically. Let's start with a column count of 1, and then I'm going to repeat doing this until the column count, then my overall count. And when you do this, you say while. So this is a repeat while statement. Most languages have a while or do repeat or do until. This is repeat while. So it makes no sense to add so many columns that it's more than the number of items that I have. It's not going to help at that point. And inside here, I'm going to get the width and height of each of my cards or cells really in this, given the number of columns that I have. So the width is just the size that I've been offered divided by that many columns. Everybody agree with that? And then the height is just the width divided by the aspect ratio. That's how I get the height of each cell. So now I know the width and height of every cell if I had that many columns, that column count. Now I'm going to get the row count. I'm going to say, well, how many rows would I need then if it was that size? And the row count is just the count divided by the column count, but I need to round this up. If I had 3 things and I had 2 columns, 1, 2, 3, that's 2 rows, not 1 row. So I need to round this up. Dot rounded is just a function in CG float or in double. And it rounds it. You can round up, you can round down. There's various arguments to this thing. It's got an enum here. So now I know the row count. So I'm going to say if the row count times that height of each cell is less than the size that I was offered's height, then I'm done. I win. And I'm going to return the size dot width divided by the column count. And this one also I'm going to round down. One thing about SwiftUI that is super cool feature is it draws on pixel boundaries. That's not the same as point boundaries. All the work we do is in points, all these things. And a point can have 1 pixel to it or 2 pixels or 3 pixels. It depends on how incredibly dense and beautiful your retina display is or whatever. So, new iPhones, they have 3 pixels per point. So they draw very smooth lines. Old iPads, 1 pixel per point. So the lines might be more jaggy. But you don't have to even think about that. The only reason I'm rounding down here is I just don't want to have a rounding error push me over the edge, okay, where it's adding the columns. I have like 7 columns and adds numbers, and a rounding error causes it to go 1 too many, and now it doesn't fit. So I'm just rounding down to make sure it fits. It has nothing to do with pixels and points there. If that doesn't work, then let's go to the next column count plus equals 1. Now, if I get all the way through here and I've tried every single column that I can all the way up to my count of items, then what am I going to return? Well, one thing I could return, you might think here, is the width divided by the count. Take whatever width I have and then just divide it up by however many items. But that actually is not good, because what if, again, our aspect ratio is such that if I use the entire width, now my cards are all too big, you see? So I have to do really the minimum of this or the size dot height that I was offered times the aspect ratio. And I'm also going to round that one down too. So this is to make sure that it fits for sure, that these cards will fit. That might make it so that it's fewer than the entire width, even though it's 1 card per column, but that's what it has to be to make them fit, then that's what it has to be. Now I'm getting all kinds of errors here. Why am I getting all these errors everywhere? Let's look at it. It says binary operator slash divide cannot be applied to what? CG float and int. Indeed, Swift does not automatically allow interoperation between ints and floats. It wants you to think about that when you do that. What do you really mean? And now it will allow interoperation between floats and CG floats, though. CG floats are the floats that we use when we're drawing, right? You've seen those all over the place here. CG size, that's got CG floats in it. So you can do that, but you can't do ints. So how am I going to fix this problem here? Well, this one is the size.width divided by the column count. I'm just going to turn column count into a float. So I said column count is 1.0 instead of 1. Well, that fixed that problem. But there's still another problem. This count is an int, right? The count, the number of items, it's also an int. So how can I do that? Well, watch this little trick. I'm going to let count equal a CG float that I make out of the count that was passed to me. A couple of things going on here. One, you're seeing how to do type conversions. which is you just create a new one, and hopefully the thing you're creating has an argument, which is the other type that you want. And that's what's happening here. CG float, it has an init argument that takes ints. It'll do it. But the second thing I'm doing is I'm creating a local variable count that's the same exact name as a parameter that was passed to me. And it's kind of overriding it. And that's scoping. That's the normal Swift scoping there. This right here, its type is CG float. This is the argument passed to me. It's an int. And that's perfectly fine. Now, I don't usually recommend you picking the exact same name as a parameter unless it's semantically identical, which it is in this case. It's the same, it's just a different type. So I think we're okay to do it there. And that's it. This is our little simple way of calculating the size of the cards. So let's hope it works. No errors. Seems to be doing it. Let's go over here and pick some different numbers of cards. Let's try what happens if we do one card. Now, our model is smart enough to say, oh, you can't have a matching game with one pair of cards, so I'm going to make two. So that's why we got two there. And these cards look good. Yeah, look absolutely fine. How about two? That's going to be the same as we just had there. Three. Oh, look at that. Resize the cards to be smaller. Four. They didn't need to be smaller. Five. Resize it smaller again. 6, 7, 8. Size is fine. 9. Fine. 10. Okay. 11. Oh, smaller again. 12. The reason it's switching back is because I'm hitting backspace and now it's going back to 1. And that's because the previewer is so fast it's able to rebuild and get it going there. But this is working great. So we don't have to ever scroll here. And we have essentially used this geometry reader to look at the space that was offered to us and pick an item size that makes them all fit. I'm going to do one other thing here. It's kind of a transition into our next little thing, which is, you see this 2/3 right here? I have that magic number in two different places. We're going to talk about on Wednesday blue numbers. This is blue. This is blue. Blue numbers are bad. Blue numbers are magic numbers. Surely you've all learned in CS106 or whatever. You don't want to have magic numbers. You want to have constants for those. So we're going to talk all about how we do constants in Swift on Wednesday, but I'm going to do just this one constant here. And I'm going to do it by going up here and saying, let aspect ratio, which is the CG float, equal this 2/3 thing right here. And then I'm just going to replace everywhere the 2/3 appears with this aspect ratio. And this is nice. Okay, this makes my code not most nice. Oh no! How could that possibly have broken something to do that? Let's take a look. What does it say here? Function declares an opaque return type but has no return statement in its body from which to infer the underlying type. What this means is, you said this returns some view, but I'm looking in here, I don't see this thing returning some view. And in fact, this doesn't return some view. In fact, this is not even valid syntax. It doesn't return anything. It just has a little let there, and then it just has a view sitting there. It's not returning that view. Now, you might be saying, wait a second, well, you do this all the time. In our view builders, we're supposed to be allowed to have variables and then just list views. How come it's not working? Well, the answer is var cards, that computer property, is not a view builder. It's just a regular function. So we could fix this by saying return this. That would work. Now this is a normal function that just is declaring a variable and returning some view. But we would probably not do that here. Instead, we would turn this var into a view builder by saying @view builder. Putting @view builder in front of a var says, look at the contents of my computer property here as if it were a view builder. That's what @view builder does. Now, you might say, why didn't we put @view builder up here? @view builder. Well, we didn't have to because the person who designed that protocol did it for us. Right? We only have var body because of that :view up there, behaves like a view. So this is implicit with var body. That makes sense. Whoever at Apple wrote the view protocol, they knows that your var body always wants to be a view builder. But you can do it for your own ones as well. Now, having said that, I probably wouldn't do this. What I would do is take this aspect ratio and put it out here as a private let constant, because aspect ratio is an important thing in my view. The aspect ratio of the cards, that's important. I don't want it buried as a local let in some function. I want it up at the top level so that readers on my code can see, yes, I'm building a memory game with cards that have aspect ratio. I might even want to rename that to be card aspect ratio, to be clear. It's the aspect ratio of the cards, but we'll leave it as here. By the way, I've noticed I put private there. In our view, and generally, whenever we're programming in Swift everywhere, we put private in front of everything, unless it needs to not be private. Now, why doesn't var body have private? Because var body is part of the view protocol, and in the view protocol, it's not private. So we can't make it private if it's not private in that protocol. All right, so we learned a little bit about view builder there, that we can take a function or a computed var, either one, and put @view builder in front of it, and then the stuff in there will now be interpreted as a view builder. So let's go back to the slides now and talk a little bit more about view builder. We already know what a view builder is. It's just this way to have a list of views with conditionals and little lets. That's what a view builder is. It takes a function that returns a view and it interprets it in that way. The reason we need this is a lot of times we have bag of Lego views, which are a bunch of views, but we want to pass them around as a view. And that's why in the very first lecture I said, bag of Lego, this is a view. And I tried to plop it on top of the Lego I was building. That's why we have view builder. So we can combine a bunch of views together and make a single view out of it. That view we learned is often a tuple view. So tuple view is just a view that can contain a number of views. By the way, tuple view isn't infinite. I think it's like 11 or something like that. You can have up 11. If you had more than 11 views, you're probably going to use a for each to do more than 11 and put the things in an array or some sort of thing that drives it. It also might be a underbar conditional content. I think that's still what it's called. I don't think they've made that really a public thing. When you see underbar in front of something, that means it's not really public. You're not supposed to use it. That means you would never use conditional content yourself, but the view builder uses it when there's an if-then or a switch or something. It's using conditional content view. And it could also be empty view. Like if you have an if-then and the else case did nothing, then it might be an empty view in that case. And it could be any combination of these things. Tuple views with conditional views in there, conditional views with tuple views, any tree of these things that you want. It all rolls up at the top level. There's either a tuple view or an underbar conditional content view, or something's at the top level. That's the view that's returned. That's what's going on inside View Builder. Now, I'm not going to talk about how it does that. It's actually a public mechanism, how it does it. You could go and look at that if you wanted to build your own something that parsed the stuff inside of a function and did something with it, but way beyond the scope of this course, right? Now, what it creates, we really don't care what it creates. Some view sets it up for us, so it's completely meaningless as to what it creates. But we do sometimes want to say which of our functions that return a view get treated as view builders, and we saw already that any computed var or func can be marked as a view builder. And here's my example of it. Let's say we had a function for the front of our card. Right now we embed it all in our var body, but let's say we had a function for it. We couldn't just do front of card, some view, shape is round, rectangle shape, stroke shape. So we can't list the views like this. But if we put @view builder in front, woohoo, and now green light, we can do it. That's exactly what we just did in our demo. And this thing right here would return something tuple view with 3 don't cares, rounded rectangle text. So it does this with generics. Tuple view as generics. You can have up to 11 don't cares right there. It doesn't care what they are, and that's what the views are. I'm not showing you this because you're supposed to know this. I'm just showing you how weird it is and why you don't want to know what it is and you don't care. It's just some view. We saw how we can turn a function into a view builder. We can also use it for argument types. If we're passing an argument, and this is how a Z-stack works, right? When you pass the content to a Z-stack or an H-stack, it's a view builder. Well, how does it do that? In their init, they mark that argument as @view builder. And we're going to do this also in our demo. It's really simple. You just put that @view builder right before the argument in your argument list. You can also do it with a var. So if you had a view that had a var that was a function that returned a view, it could just mark that var as @sign view builder. And then you wouldn't even need the init. People could call it, they would get the free view builder activity going on their function. Just to reiterate, view builder, it's just a list of views. It's not arbitrary code. You can do the ifs, you can do the lets, and that's it. Let's go build our own HStack, VStack-like thing. I'm going to build something that does the cards. So it's going to be a generic view that takes any number of items and a view builder for each item and lays them out at a certain aspect ratio so that they fit. All the stuff we just did, I'm going to put it in its own little HStack-like deal. Let's see what that looks like. Let's start by creating this thing, or start trying to create it. It's a view. HStack is a view. All these things are views. So I'm going to say File, New File. And when I do File, New File, I'm going to pick at the bottom left SwiftUI View. See that? Because this is a view. So here we go, SwiftUI View. And what name does it have? I'm going to say Aspect VGrid, because it's going to be a VGrid, but it's going to use the aspect ratio to make things fit. So it's an aspect ratio oriented vertical grid. One thing, this is great. I'm really always going to check this group. Every time I do this, I'm going to remind this because I know you guys, you don't check this and then files end up all over the place at your top level and stuff. So you really want to put this where all your other files are, and you want to put it in the group here so that when you look in your navigator, these files won't be all over the place. They'll be collected together. So here's my aspect VGrid. It's created. There it is, where all the rest of my files are. It's created it here as a normal view with a var body. Let's get rid of our preview. If you built your own A-stack or B-stack type thing like this, you would have a preview and you would build some kind of sample content that you would use to show if your thing is working. We don't have time for that, so I'm just going to delete the preview. So we're not going to be able to preview this aspect VGrid, but we will be able to preview it because we'll be looking at this pinned view, which will be using it, so we'll be able to test it there. This aspect VGrid, I could do it as a custom layout. Remember I told you that there was that thing where the dance of how much space you're offering, what size are you, and I'm positioning you. To do that, you just say that your aspect VGrid implements the protocol layout. Now, a layout is a view, so you're still behaving like a view because a layout behaves like a view. And when you do that, if you want to see what it looks like, let's go here where it says, oh, you don't conform, and let's look at the protocol stubs. And I'm not going to implement this, but you can see what it looks like. Size that fits. Here's my subviews. Here's the proposed sizes. Here I'm, after the fact, being asked to place my subviews based on their proposed size and the sub. See how it works there? This is all the mechanism, really just these two things. Now they're being called back and forth. You're calling them, trying to size them. They say no. You offer different sizes back and forth. You keep working on it until you get what you want, as close as possible, and then you place your subviews there. And then you can size yourself. Everybody can do that. So that's what it looks like, but we're not going to do it that way. We are going to implement our aspect VGrid in terms of our lazy VGrid because we've already written that code, so we'll just use it. And this is what I mean by that. I'm going to go back to my view here, and I have all of this junk. Look at all this junk from the geometry reader all the way down to this for each. I just want to get rid of all of that. Cut it out of there, and instead I want to say aspect VGrid with these cards with an aspect ratio of my aspect ratio. And then all I really want to have in here is my cards. See how beautiful this code would be if I only had an aspect VGrid? So let's go make that aspect VGrid. I'm going to go back here to aspect VGrid. It has a var body, just some view, because I'm not using that layout thing. I'm just going to paste what I just copied out of there into here. Now I have to fix this up a little bit because it's referencing things like my view model. My aspect VGrid can lay out any array of things. It doesn't have to be cards or anything. It's a generic HStack-like thing. So I'm going to have an array here called items, which is going to be an array of some don't care. I don't really care what they are. So let's put our don't care. We all hopefully familiar now with don't cares. So I'm going to use those items instead of my viewModel.cards. Where I say viewModel.cards here, I'm going to say items. count. And same thing over here, my for each. I'm going to for each over the items. And let's put some curly braces in here. Grid item width that fits. Let's go grab that. That's the function we wrote that does the math. That. Let's see, our little emoji memory game is looking really nice right here. Let's go back to our grid. Let's put that as a function in here. This is item in. Now we've got the dreaded error, failed to produce diagnostic for expression. Please submit a bug report. When you get this is one of the most frustrating things to get in SwiftUI, actually. What this is saying is there's some problem inside of your view builder, but since it's deep in a view builder, I can't tell you what it is. This is one of the reasons we try to have nice, small, little, computed vars and functions for all our views, not these big, massive things. We want to break it up into little pieces like we did in the very first lectures. Remember, we broke everything down, like when we were doing the plus minus buttons and all that, we broke everything down to 1 and 2 liners. That's why. If we have a big one with a lot of lines, we don't know what's going on. Now, I happen to know what the problem here is. This aspect ratio right here is not defined. That needs to be an argument to my aspect vgrid, of course. So I'm going to have I'll have it be a var aspect ratio. It's a CG float, and I'll have it default to 1 even. Just have a nice default. Why not? That fixes that. Down here, we got another problem. This one, at least, we know what it is, right? Referencing initializer init on a for each requires that item conform to identifiable. That's what for eaches do. They for each over identifiable things. So this don't care that we have up here, it has to be an identifiable, where item is an identifiable. By the way, there's another syntax for this. If you don't want to do this where, if you just take this and pop it in here, then that means the same thing. So that's aspect vgrid. It has a don't care that has to be an identifiable, and it itself is a view. Now, if we go back to our memory game view, we're almost there. We'd have to put items as the name of this argument, but we've got another argument to our aspect vgrid that we're doing nothing about, which is the card view to show for each of the things in the aspect vgrid. So this is the thing that's on the end of an H stack, it's on the end of a V stack, it's on the end of a Z stack, it's the thing we want to be a view builder. It's the view to use for each of the cards that the aspect vgrid is going to do. So how do we pass this argument right here? Let's go back to aspect vgrid. It's going to be some argument, so it's got to be some var here. We'll call it content. How about that? And what type do you guys think this var is? How about a function that returns a view? Well, we're getting there. It is a function that returns a view for sure, but a couple of things about it. One, you can't say returns a view because view is a protocol. And you need a concrete type there, an actual type. And you might think, well, how about if we say some view, okay, like we do var body? But there's no curly brace thing to look in and see what type it is. So can't do that, can't do some view. So you know what we're gonna do here? This is gonna return a don't care called item view. So I'm gonna add another don't care up here, item view, and it's gonna be a view, something that behaves like a view. Now, there's one other thing about this is that I need to pass the item that I want you to make a view for me here along. So this has to take an item as an argument. So that almost is what it looks like inside ZStack and HStack when they're taking that content argument from you. They're just saying, give me a function that returns a view. And for HStack and VStack, it has no arguments. For each, it has the same thing, and it does have an argument. The for each has the iteration variable being passed to you. And our aspect vgrid also has that iteration variable that we want passed. Now if we go back to here, oh my gosh, it compiles. Because here is a trailing closure that takes one argument, passing it. I'm giving you a view. This is identifiable. We satisfied all of our constraints on our don't cares up there. You see, I'm setting the aspect ratio of my card view here, but I'm also forcing that aspect ratio on the V grid. So let's let the V grid do this aspect ratio setting on the view. I'm going to take this aspect right here, put it over here on this thing inside of my view. So what goes in here, this for each? I'm doing for each over the items. I want a view for each item here. And real easy, I'm just going to content the item and do that aspect ratio. It worked. Content is just a function that takes an item and returns a view for it. So saying content of item gives me a view. I set its aspect ratio to match the aspect ratio I'm doing the calculation on. Voila. Any questions about that? Make sense? Oh, back here, why did we get rid of the outside view builder here? Because we only have one thing in here, and so it's just returning it, so it's normal function. Doesn't need the outside view builder, although I'm getting to that because I'm going to make it need it in a second. Any other questions about what we did so far here? All right, so let's talk about what she said. We don't need an outside view builder here on our cards. And actually, we didn't need an outside view builder here either, because this card view is just one view. It returns it. There's really no need for a view builder. If you want to really think about it, this is just the same as saying return card view. So this is a normal function. This is not a view builder. And if you look over an aspect V grid, there's nothing that would say that it's a view builder over here. I don't see the word view builder over here, so it's not. And that means if I tried to do view builder things in here, like watch this. Let's go back and put our V stack. Remember the V stack that we had where we had the card view and the card's ID when we were learning about identifiable? Remember that? We have these little IDs, A1, A2, B. What if I said, well, I only want to see the A cards. I'm debugging it, and I just want to say if the card's ID last is something that just gets the last character, equals B, then show me this. Otherwise, I don't want to see it. In other words, filter out the A. Uh-oh, failed to build, doesn't work. We get this dreaded can't conform to view. That's because this is no longer a view. In fact, this is not even returning anything at this point. It's just got an if. It never returns anything. But it is a valid view builder, right? It's got just if-thens and lists of views. So we need to make this function take a view builder, and then this will just work. So how do we do that? We go over to our aspect V grid. Here's where the function is. It's this var. I'm just going to mark this var as an @view builder. The @view builder works not only for vars where the computer properties, but vars that are passed into something also can be marked view builders. And when that thing is passed in, the compiler is going to run the view builder magic on it and look at it and interpret it as a view builder and turn it all into a single view. And so this is going to get turned into an underbar conditional content, and inside it's going to have a card view, or a VStack actually, VStack with a card view. And look, only the B's. See, no A's over there. It works perfectly. Now there's one other problem I don't like here. You see this says items. Really, it'd be nice if I could do that thing where I don't have to say items. Wouldn't that be cool? Y'all remember how we did that? We go over to our view and we just create an init. So I'm going to create an init here and got to fix it up a little bit. My items are an array of items, and this function takes an item and returns an item view. One thing I'm going to make sure I say here, because I know that some of you are confused by this. You see I say self.items equals self.aspect ratio is self.content. I see a lot of you in your inits, in your assignment, saying self.something equals all the time in your inits. Totally not necessary. The only time you need to say self.items equals something is if you're going to say it equals items, because Swift needs to know, when you say items, do you mean this items or do you mean this items? You see? And self.items is this items, the items on myself, and this items is this items. So that's the only time you need to do self.thing equals is if you're setting equal to the same named thing. It's just telling the difference. Otherwise, you don't need self.. And then I can just do my nice underbar. There we go, right? Underbar items. And that should work, right? Let's go back over here. We're back to type cannot forms a view, just as if it doesn't think this is a view builder anymore. And in fact, it's not a view builder anymore because our init does not take a view builder as an argument. So it's passing this through as a normal function. And so it never gets view builderized by the time it gets to that @view builder var. It's been deview builderized because it's been passed through. But we can make it happen by just saying that this is an @view builder argument. Now, this argument will do the view builder processing when the thing is passed through. And in fact, if we do it this way, we don't need the one here anymore. Because view builder processes all the information inside of a function, turns it into a view builder, it really kind of creates a new function that returns a view. And that view has got a tuple view, content, conditional content, all that stuff in it. And that's the function that gets set into that content right there. It doesn't hurt to have this view builder thing back here because this view builder thing that this builds is compatible with assigning it to a var that's a view builder, obviously, but it's not necessary if you have an init. So we've seen 3 places that view builders can go: on functions, on the arguments to functions, which will make it so when the function is passed in, it gets view builderized, or on vars that are parts of struct, in which case when the var gets assigned, it'll get the view builder treatment. And we can go back to this and get rid of all this extra stuff we put in here. It still works fine because it's still a view builder. The reason I show you all this is I want to give you a little exposure how this stuff, view builder and the arguments to ZStack, how those things are actually working. I'm not showing you this because you're going to have to do this. In this class, you will not be building your own aspect vgrid, but you'll be using a lot of HStacks and VStacks and lazy vgrids, and now you understand how they work. And the same thing's going to be true on Wednesday. We're going to talk about view modifiers. Right? We have all these view modifiers. How do those work? I'm going to stop there. What we didn't get to today, we didn't get to drawing your own custom shape. You will need the shape for a very small part of your assignment 3. So you can start on your assignment 3 and just don't do the custom shape part. Just use some other shape until we go over it on Wednesday.